This is Sanity Checker, a Python library built to allow researchers to evaluate deep neural network interpretability tools. Effective interpretability and explanation tools are increasingly vital in today's society. Interpretability tools can help with regulatory requirements, model debugging, and general just trust from the public, and also revealing bias. And the issue at hand is that not all of them can be easily evaluated by the researcher for the quality, scope, and usefulness of the explanations that they provide. And so you can imagine for a researcher, for example, who is building a model for a self-driving car, and the model misclassifies a lane barrier or a road or an obstacle, the effects of that misclassification would be grave. And as a result, we need more interpretability tools to be able to better debug our models and find out why they make certain decisions. So a little bit of background. Interpretability is the degree to which humans can understand the cause of a decision made by a model. So like I just said, for classification, that's a really good example because say something is misclassified, you want to know and have a better idea of why it was misclassified in the first place. Interpretability tools are anything a researcher can use to increase interpretability in the model itself. So this can include a lot of different methods. A lot of methods are being created today. A lot of them are new. It can include things like feature importance, data visualizations, rule-based classifiers, and others. It's very difficult to quantify how interpretable a model is and how to define interpretability. And there's very little consensus in the space right now on how exactly we evaluate these explanations and how to properly benchmark them. So I'll focus on one specific form of interpretability tools for this presentation called saliency methods. And they're a very widespread class of interpretability tools that are able to highlight relevant features of an input for a given classification model. So some related work for this project. First, there's a lot of work in defining interpretability in machine learning. There's also a lot of different work detailing, surveys for different tools and taxonomies of how interpretable machine learning is structured, just in general. And also, there's many examples of cases where researchers rely too much on misleading explanations, and also rely too much on tools that may end up being unreliable for the given task at hand. The saliency methods that I talk about originally started from a deconvolution neural network procedure that was mainly used to interpret image classification models, although these saliency methods can now be applied to many other different forms of machine learning. So much of this work was based on a paper by Bean Kim, who performed sanity checks on saliency maps. And so this is one of the figures from their paper, and it does a very good job of showing all the different types of interpretability tools that can be used. So a lot of these along the top are gradient-based methods, and right now it's working on a different classification models. And so you can see that a lot of these different gradient-based importance tools have different outputs, but some of them have very similar outputs to this simple edge detector here. And that's very interesting since the edge detector does not depend on the model that is being currently used for classification. And it also doesn't depend on the data either. It just solely depends on whatever this picture looks like. So the target task for this project is to provide researchers with an easy way to evaluate interpretability tools, and also the explanation methods that they use so that they might provide more insight into the models that they are building or working with. And so once again, Sanity Checker is an easy-to-use Python library for sanity checks that can integrate easily with existing models and existing frameworks. So how do we actually perform evaluations? Well, there's 3 steps. The first is to calculate the actual explanations for an unchanged model. Then we take and perform perturbations or randomizations on the model weights or the data that the model was trained on. And then lastly, we re-examine how those explanations differ for the randomized or perturbed model and the unchanged model. So a sanity check in this case is really that we expect the explanation to differ greatly if we change the model or the data that the model is trained on by a lot. So first step is the explanations. The sanity check library currently supports 6 different types of gradient-based explanations. So we can imagine, say for example, a simple classification function from Rn to Rc, where n is the dimensionality of the input and c is the number of output classes. There are a lot of different variations of the gradient-based saliency method that we can use. So saliency is just a very simple single backpropagation pass through a convolutional net to compute the gradient with respect to the input. So that's really the basis for a lot of the different gradient-based methods that we're going to talk about. And so gradient x input and integrated gradients are variations of that calculation. And so are these other variations of ELRP, guided backpropagation, and guided GradCam. So the second part is actually performing the sanity check. So the first type of randomization that we'll go over is complete model randomization. So what this does is it just randomly permutes the weights for each layer in a trained model, and it basically allows the model to keep the same structure. We reinitialize the new weights uniformly from -1 to 1. And this type of randomization, basically we should expect that for a task where the researcher is trying to determine explanations relating to the weights of the model, we expect that if we randomize the learned parameters, that the explanation should change a lot as well. So basically we can be sure that if we have randomized the model, but the explanation still doesn't change very much, that the explanation tool that we're using doesn't have that much reliance at all on the learned weights, and thus it might not be suitable for the task at hand. The second type of randomization is cascading model randomization. It's very similar to complete model randomization. The only difference is that we gradually randomize the model layer by layer, starting from the bottom up, to kind of see how the model or the tool that we're using responds to randomization over time. And so after randomizing each layer, we compute the explanation again and compare that with the original. And we do an analysis on that, which shows how the how the tool deals with progressive randomization. So lastly, we have data randomization. This is a method of randomly permuting the training labels of the input data before retraining the model and recalculating the explanation for those given inputs. And basically for a meaningful explanation here, just like the first two, we expect that if our explanation tool should highly depend on the training data of the model, that our computed randomized explanation in the end should differ a lot from the original explanation that we started with. So if our task requires that our explanation is related to how the model was trained, then our explanation should differ when the data differs. The third part and last part of our sanity checker is our similarity metrics. So we have, up to this point, methods of computing an explanation. We have methods of randomizing a model to see how the explanation changes. Now we need ways to compare two different explanation scores and see how the effects really differ. So the two methods that we're going to use, the main one is Spearman rate correlation, and the second one is a simple mean squared error. So implementation, what do we need? The requirements of this project were to make it as modular, as the library as modular as possible, which means that classes are functionally independent, to make the library extensible, which means that it's easy to add new classes for evaluations, easy to add new similarity metrics, really just be able to extend the different methods that we're using should we need more in the future. And the third is that the model is easy to use. So we'll go over a demo where we see that it takes very few very intuitive API calls to use the library and get the results that we want. So as for actual implementation, we have gone ahead and just abstracted the classes for explanations for different ML frameworks, randomizations, and similarity metrics to compute two scores. The abstractions make it easy to extend and make the code very modular. And on top of that, we add support for showing visualizations for whenever we run our different evaluations. So this is the abstraction for explanations. We basically provide an enumeration of the different options for computing the explanation we support. And you can provide that to an explanation class. You can provide any number of different explanation methods that are supported to be able to run with a sanity checker. And so the explanation object simply takes in the data and the model, and then you can run an explanation for the list of explanations that you've chosen. For randomizations, our sanity checker takes in the different model types it supports for prediction. Right now, the best ones to use are Keras and TensorFlow. And so when we call evaluate, we basically provide the randomization that we want, the explanations, and the similarity metrics that we want to use. This makes it very easy to use the library in one call. It gives the researcher a lot of different flexibilities and configurations that they can use to really allow this tool to be best used with whatever research or whatever goal they're trying to accomplish. And similarities is very simple. Basically operates on a score matrix, on two different score matrices of the same size, and it computes the comparison value between the two. So we conducted a few experiments with this. I'll go over two right now. The first is a very classic machine learning setting with the MNIST data set of handwritten digits. It's a set of 60,000 training samples of size 28 by 28, and it's a classifier that tries to identify which digit is in the given image. And so we were able to train this model for greater than 97% accuracy. Our second model that we're using is actually an online hosted model for genomics and DNA sequence classification. So we ended up using 5,000 sequences from a DNA data set where each sequence is of length 101, and there's 4 different types of characters that can be in each place in the sequence. So this is a good example of a non-traditional use case for saliency methods that still works with those given explanations. And it's just a very new way of using this discrete sort of model as opposed to a image-based model. And so this is the first graph of the results from the CNN. And as you can see, this chart is of the layer by layer cascading random model randomization. And so on the y-axis here, we have the actual rank value, the rank correlation between the originally calculated explanation and the new explanation after a layer has been randomized. So you can see that if we are expecting to use an explanation and have it relate to how the model was trained and the model's weights, then we expect that with more and more randomization that the rank correlation between the randomized explanation and the original explanation goes down to 0. And so that's what we see with the majority of these methods. So saliency, ELRP, and integrated gradients and gradient input all end up going around close to 0, or at least very far away from 1, which is the saliency, or which is the sanity check that we expect. However, we noticed that if we had used guided backpropagation and guided GradCam, that they don't really respond at all to our randomization. So that suggests that these tools right off the bat may not be suitable for an explanation task that requires us to depend on our model parameters. Very similar to the previous results, we get a rank correlation here for DeepBind where, as we see for many different explanation methods that we've chosen, that there is a gradual randomization in how the tool responds to our cascading layer by layer randomization. However, for guided propagation and guided GradCam, the results don't really change, and as we can see, these might not be useful for our given use case. So this is a summary of results that we've attained just through complete randomization and also randomization with our data. So we expect that with increasing data randomization, if our tool is sensitive to that our once again, our rank should go down to around 0. And that's what we see for many of these, except for backpropagation and GradCam, which are not sensitive at all to our randomization methods. And so it's a lot clearer to see how this works in a short demo. So we have a online Git repository with a Python notebook that shows that demonstrates how to use the tool in a CNN setting. So this is just very simple code that was obtained online from Keras for training a MNIST classifier. And so basically all this does is just pulls in the data. And what we do right here is we actually load a saved model that already has pre-trained weights. And so if you have that, you can immediately begin using the explanations. So here I initialize the explanations to whichever ones that I want to support and run in this evaluation. And so this is just one line of initialization, very easy to do. And then again, the library calls are very short. We just initialize a new sanity checker with our given model, and then we call it evaluate. And we can provide as many different similarity metrics as we want. Right now, we're picking both MSE and Spearman rank. And then we're going to run a complete randomization, and the library will automatically show the results for the given explanation method and the given randomizations. So here we have rank and MSE. The MSE is not super useful to us here without looking at maybe a normalized version. However, the rank here suggests that maybe for backpropagation that there was no real sensitivity to the randomization. Another feature that we have is cascading randomization, which prints out a layer by layer graph of the randomization as we perform calculations. So here we have a friendly, Excel-friendly chart to print out, and also we have the results for each different method for each different layer printed out as well. Lastly, we can compare results with randomly permuted labels, and so this allows us to also see the same results in a friendly bar chart. The command line is also available for this library. However, we do recommend using it as seen in the notebook, as that allows for a lot more customizability. So challenges with this project is very difficult to implement all the different explanations. Had to rely a lot on external libraries and their implementations of these explanations. And a lot of those come with different performance costs. Another one, it's very difficult to generalize to ML frameworks, as I learned. So having to replicate all of the Keras functionality for PyTorch would have taken a lot of work. And that's why Keras right now is the most highly supported framework for this library. And so in conclusion, our goal was to provide researchers with an easy way to evaluate these interpretability tools and the explanation methods so that they may provide more insight into the models that they build. And we successfully implemented an easy-to-use API that researchers can use with their existing models. And so for future work, improvements can be made definitely to the explanation methods and the supported model frameworks. We're always looking to add more to this library and make it a more comprehensive tool. The performance of the evaluation calculations are actually very expensive, and they can also be improved in the future, probably with more proprietary calculations rather than relying on external libraries that may have more overhead. And also, We'd also like to add more complex evaluations for benchmarking. Right now, it's just a sanity checker, like we're just doing randomizations and expecting our results to be very random. However, there's likely more complex evaluations that we can use for benchmarking in the future. Thank you.